Today's video, we're going to be talking about Euler's formula. So the idea is, and I'm presuming that you've come into this video with some idea on how to add, subtract, multiply, possibly divide complex numbers. If not, I suggest going back and brushing up on some of those skills. But we want to now figure out, what does it mean, what should it mean to look at powers, exponents involving complex numbers. So we're going to start out somewhat small, looking at how to evaluate real number to a complex power. And because we could work our way around to this, no matter what real number we start off with, the most natural choice, the thing that's going to help us most, is figuring out how to evaluate something that looks like e to a complex number. Even that is a bit ambitious for this video. We're going to simplify things just a little bit more. We've got something, if we just had e to the, by setting usually the way to make a complex number look simpler, or to deal with a simpler case involving complex numbers, we know if we had b being equal to 0, that this would just be e to the a, that would be e to a real number. That wouldn't be anything new. Our simplest case that still deals with complex numbers is going to be to figure out what it means to evaluate e to the bi. So now, in some senses, this is new material. We get to define it how we want, but we'd like to figure out something that makes sense with previous rules. So one previous rule, the one that's going to help us most, we don't have any intuition what it means to multiply e by itself, b times I many times. So we're going to look at a more complicated rule about the function e to the x for some real number x, see if it would make sense to extrapolate that to the complex case. Specifically, I am referring to power series. We know that, if x is some real number, there is a Taylor series that converges to e to the x. Might as well go with the Taylor series centered at 0, Maclaurin series. If we look at this infinite sum from n equals 0 to infinity of x to the n over n factorial, no matter what our x is, this is going to converge to the value of e to the x. This is super useful because it gives us a way to evaluate e to the x, or at least figure out something that would align sensibly with evaluating e to the x, without actually knowing how to raise something to a new power. We do know if we have a complex number here that we could just say that e to the z, where z is a complex number, we replace all of our x's with z's. So let me go back and actually say what I'm trying to say. So what if we were to say that to find e to the z, we just fill in this complex number. So we'll go from n equals 0 to infinity, z to the n over n factorial. The operations needed to involved in evaluating the right-hand side of the equation would just be multiplication of complex numbers, division by real numbers, and then addition of complex numbers So we could at least find all the partial sums of the series. Question would be, does this make sense? Does this converge to things? Does it converge to sensible things? But that's where we're going to plan to go see what happens. So again, here we said that z was any complex number. To make life easier, let's see what happens when we just use something that looks like a pure imaginary number, b times I. So we're going to have sum that looks like b times I to the n over n factorial. If we expand this a little bit, it looks like we're going to get something that looks like first few terms. So if n equals 0, we'll just have b I to the 0th. Anything to the 0th should be 1. So we should just have b, and then b times I over 1 factorial, 1 factorial, which is just 1, b squared I squared over 2 factorial, etc. And maybe I'll go one more. So we'll have b to the 4th, I to the 4th over 4 factorial, keep on going. So to figure this out, we should think a little bit about what I to various powers are. I said already that I think I to the 0 ought to be 1 just based on exponent rules for real numbers. I to the 1st, of course, should just be I. I squared should be I times itself, square root of negative 1 times the square root of negative 1 is going to get me negative 1. I to the 3rd power, we could say that's I times I squared. We know I squared is negative 1, so this should get me negative I. And then I to the 4th power, that's the same thing as I squared squared, which is going to be negative 1 squared, which is 1. We've looped back around. As we keep on adding more powers, we're going to keep on cycling through this pattern of 1i, negative 1, negative I. So in the series, we have some I-related terms. We have some terms that are going to go away, though. So this is going to look like, we'll have b times I over 1 factorial. I'll write this over 0 factorial. This is the case where simplifying less may be more helpful. I'll have minus b squared over 2 factorial minus b to the 3rd. I to the 3rd is negative I, so b to the 3rd times I over 3 factorial plus b to the 4th, I to the 4th is just 1 over 4 factorial. And then we'll keep on going. B to the 5th would be multiplied by I. And then we'd switch back to negative minus b to the 6th over 6 factorial minus b to the 7th times I over 7 factorial, etc. So, analyzing this, we can see some pretty clear patterns. We're alternating plus, plus, minus, minus, the power on b, which actually, it looks like I did something wrong over here. this should just be b to the 0 should just be 1. So let me translate that down here. So power on b keeps increasing, the factorial in the denominator keeps on increasing, but we've got this plus, plus, minus, minus, plus, plus, minus, minus pattern going on, and odd terms have an I accompanying them, even terms don't. It's not always guaranteed that we're going to be able to do this, but power series for e to the x is nice enough that we can. I'm going to split this up, collect together the terms that involve I and the terms that don't. So we're going to have 1 over 0 factorial, which is just 1, minus b squared over 2 factorial, plus, these are all the terms that don't involve I, minus b to the 6th, etc. And then we've got, essentially, that's our real part of the final answer so long as everything converges. And then the stuff involving I will give us the negative, or sorry, the imaginary part of our final answer, again, assuming everything converges. So here we'll have b over 1 factorial minus b to the 3rd over 3 factorial plus b to the 5th over 5 factorial minus b to the 7th over 7 factorial if you know your power series, this is something significant. Here we've got only even terms, they're alternating. This is the power series for cosine of b. So this is cosine of b. This part here, the I gets carried along. These terms, this is the power series for sine of b. So even though we hadn't originally known how to exponentiate something that looks like e to the I times b, we're forging new grounds, we're making new rules. It really just kind of makes sense, and it would fit very well with the power series definition to say that e to the I times b is equal to cosine of b plus I times sine of b. So we're going to take this as our way of computing e to the I times b. It gives us a very straightforward means of doing that without needing to resort every time to power series. So we take this as our definition. So using this formula, see what we would get if we wanted to find e to the I times pi over 2. That's going to give me, we're going to say that this is going to be cosine of pi over 2 plus I times sine of pi over 2. Cosine of pi over 2, thinking unit circle, is just going to be 0. And then we've got I times sine pi over 2 is 1. So this is just going to be I. Something like e to the 4 pi over 3. We can keep on using our formula. E to the I times 4 pi over 3 is going to be cosine of 4 pi over 3 plus I sine of 4 pi over 3. So we end up with cosine of 4 pi over 3, we would have 4 pi over 3 is somewhere around here on the unit circle, so cosine is negative 1/2. And then we'd have negative I times the square root of 3 over 2. How about something like e to the I? This seems like an obvious thing that we'd want to try to evaluate. Unfortunately, it doesn't look very nice. We end up with, this is the same thing as I times 1, so we would have cosine of 1 plus I sine of 1, not really knowing exactly what cosine of 1 and I sine of 1 are. They certainly aren't nice numbers, but that is what that is. So for your exercise, I'd like you to evaluate e to the pi I over 3. To conclude this video, though, I would be remiss if I didn't look at one particular special case. E to the I pi. Based on the formula, we get that that's going to be equal to cosine of pi plus I times sine of pi. So cosine of pi is going to be negative 1. Sine of pi is 0. So we get the equation that e to the I pi is equal to negative 1. You'll notice that we've got these 4 significant constants, 1, e, pi, and I, all showing up in this formula, being interrelated. This is the type of thing you can carve into your pumpkins or onto the top of your pies as you bake and impress the right people. So enjoy!